Okay, guys. So the objective for today's lecture is uh, between the last three lectures, we learned about the strategies that are deployed in HFT, the participants that are in the market, and the low-level hardware infrastructure that actually defines how we use our applications. So the purpose of today's lecture is analyzing the design of the OMS, RMS, and the TBT feed handler. All of these three components are basically the client side components, or I would say the broker side components, or when you're dealing with institutions, they're the client side components. So these are the things that you'll actually be working on when you're working in the industry. And when you're working with, for example, a company that works with HFT, they have their own RMS stack and they have their own TBT feed handler in the OMS. Also, I'll give you a lot of examples. I'll give you the production level code, some snippets, and I'll explain to you the code for the Kraken API that I work with. Exactly how I implement the OMS. I did not implement an RMS, but the OMS and the TBT feed handler part. And we'll also talk about the protocols that are used by exchanges, binary, JSON, and fixed protocols. So the objective for today's lecture is, understanding the architecture of the trading system that specifically sits on the client end, and learn about the design and code structure. Basically, the system level design that we have to implement and we have to optimize for speed, but specifically for OMS, RMS, and the TBD feed handler. We'll also explore protocol handling, so, like I talked about binary, JSON, and fix. And we'll also analyze, C++ implementation snippets that are, trimmed for performance, specifically to do the operations that are built to quickly. So I'll just move on with the next slide. Just give me 1 minute. So this is just a basic overview of the components of the HFT system. There are gateways that communicate with the exchange, feed handlers that specifically manage uh, the way the data is transferred to your application, to your strategy. And that is something that varies from exchange to exchange. Some exchanges provide streams over a WebSocket, some provide streams over binary data or UDP. And the most important part I'd say that you would have to understand from today's lecture would be the order management or handling the life cycle of a single order. Because when you place an order on the exchange, you have to constantly communicate, and the exchange sends communication to you what's happening with the order, specifically if it's partially filled, if it's half filled, and all of that information you have to relay back to your strategy so that it has a very clear and concurrent picture what's happening. And we have, I think, there are two major components for this. One is handling the updates, what the exchanges send, and one is handling, I guess, the communication part of it. The part where if a message you're sending is has failed for multiple reasons. For example, there might be a rate limit issue, or you can face any kind of problems. Your network is down, some kind of issue. Specifically, exchanges implement rate limiting very differently. NSE has a base rate limit. For example, if you're running a strategy, uh, then you have to get that strategy registered with NSE unless it has less than 10 orders per second. So if you're making more modifications than that, then that would mean that, basically you'd have to get your strategy registered. But after that, also you get limits based on the amount of money you're giving the exchange, like 500 messages per second, or 100 messages, or 1,000 messages per second. Some exchanges, crypto exchanges, or if you go around the world from NYSE, they handle it very differently. If you modify an order and you modify it concurrently, they'll basically you have a fixed rate limit, some kind of counter or some kind of tokens that you'll exhaust if you modify an order very quickly and a lot of times. So that is a very dynamic aspect of rate limiting that we have to handle when we are building an OMS for any kind of system. And talking about specifically the RMS is basically a input-output machine, but its point is to manage the state or the current balances and the current margins of the client. It has to pull those from the databases, or it can have when like specifically if you have a co-location, then it is something that's constantly it is storing, and it has complete awareness of your margins and your exposure. And the strategy module. The strategy module is something which we define. Basically, it has to have zero responsibility for any of those things. All it has to do, it has to place orders, and it has to get an updated view of the market right now. And it has to get an updated view of what's happening to its orders right now. And there's also we have to implement real-time monitoring and logging. And that is something that does introduce latency, but there are very clever ways how you can implement that. For example, you can use a static const expression, static if expressions to basically, you can compile your application with the logging, and you can compile your application without the logging. So when you're actually running in production, then you'll not be running all this logging and stuff. You'll still be doing it, but you'll defer it. But when you're testing, then you also need to have modules that can help you check where your order actually failed to be sent, or where your market data was actually it was failed to be passed. So the TBT fed handler. The TBT fed handler's role varies a lot based on the kind of data feed you're dealing with. So just give me 1 minute. I'll get my pen out. When we're talking about market data, we have different granularities of data. The first level is OHLC data, and that is of not concern to us because we'll never be dealing with OHLC data on a high frequency level. It's mostly your single minute, 1 minute, and higher up than that.
Hello, Abhinandan.
Yeah.
I think there's some issue. I think you are using not premium version of Zoom now.
No, no, I'm not using a premium
Okay,
version.
okay. Just a second. Just like you can start recording again. I'm actually allowing some more people are waiting. I'm just reclaiming the host. One second.
Yeah, yeah, sure. Okay, okay. I'll just click admit all. Can I start?
One second. One second. I'm making you a host. Yeah, can start.
Okay. So OHLC is basically open, high, low, close data. I think I think all of the people here are aware of that. The second level of data is the market depth. Now that is served differently between exchanges. For example, NSC will give you a market depth snapshot if you ever used Zerodha or any Angel Broker or any kind of API. They'll give you an exact picture of what the market depth was in snapshots of 1 second. And they'll give you the complete market depth. You can directly, for example, if you're dealing with a market depth of 10, so you will directly have the price and volume for all of those 10 levels. But when we're dealing with tick by tick data, TBT, TBT can have a multiple forms. For example, what NSE does is NSE gives you a snapshot of the market depth currently, snapshot of, for example, not just market depth, snapshot of the current orders that are open in the market. All of the orders that are present up to a certain depth that are present currently at the exchange. And after that, what NSE will do is it will give you updates in the form of order ID, which is ID, and it will give you if it is supposed to be removed, the order is supposed to be removed, or if it has been modified and the parameters that have been modified. This is a very raw approach, but this gives you a lot of information. For example, when you are building your market depth, uh, somebody is trying to somebody is trying to read my code. Saying they're still in the waiting room. Okay, so what?
Uh, Let me
Yeah,
one second. I just a second.
I don't know. Just Pranay, just can you tell me where I can like reach out to the waiting room so that if
One
somebody.
second. Actually, maybe due to the one second, I'm allowing on.
Abhinandan, I have a doubt.
Yes, yes.
So you told that we get tick by tick data and the order updates. So we get these updates separately, right?
No, no, but yeah, for example, for varies from exchange to exchange, but most of the time, the basic objective is to give you a view of the market, and then you can keep on modifying that view based on incremental updates. So you'll get
Okay.
initial view of the market. For example, if I'm joining the market at 11:30, then I'll get the view that was at 11:30, uh, 11:30 and 30th second to some microsecond or nanosecond level. But after that, I will have to use the stream to basically check. And I'll also get an update that, for example, what they do is every day the NEC starts with the sequence number of 1. So every other update you get will have a sequencing number. So you have to start listening to the stream, and then you bring up a snapshot. The snapshot will also have the last a detail about the last applied update number. And what you'll do is you'll discard the updates you received that are old, but you'll start applying the updates after that reference number.
Okay.
Yes. Yeah. So another thing that is possible is the exchange will give you a snapshot, which is very common in crypto exchanges. It'll give you a snapshot of uh, the
Yeah,
current market
Nandan,
depth.
you can start the recording. It's paused.
I think the recording is already happening.
Okay, recording happening. Okay.
Yeah, I see the red dot. So it'll give you a snapshot of the current market depth. And what you'll receive after that are not individual orders. And NSE would provide you market depth where you can have individual order. For example, if somebody is selling at a price of 100, for example, let us say this is the buy book. We have price levels here, price level of 100. And here we can have multiple orders. For example, quantity 2, quantity 3, quantity 5. And the other way you can also, if your strategy does not require this level of granularity, what you can have is just have this 100 here and this have quantity 9 here. And this goes here for the same for the next price levels. The bifurcation of your order into of your particular market level or market price into the individual orders that are actually there. And a snapshot of the current market depth, crypto exchanges provide you a snapshot of what the depth was at that point. And after that, they'll provide you incremental updates, but they'll provide you the incremental updates on this price level. They'll tell you that the price level of 100 is quantity has changed from, for example, if this order of 5 goes cancelled, then your quantity will update to 4. So yeah, these are the type of data you'll receive from the exchange. You cannot go lower than the order granularity. This most of the granularity that basically covers everything the exchange has to offer. And if you have, for example, what NAC offers, if you have other exchanges also offer that. For example, Kraken has a level 3 API specifically, and it will give you the updates to specific orders. But with that information, you can have a complete reflective image of what is actually happening at the exchange, uh, uh, with keeping in context with the latency. Apart from the latency, you have a complete image of all of the orders that are taking place at the exchange. So what we have to do is, basically reconstruct the order book, and we can store any way we want into our internal structures, anything that is necessary for our strategy. Yeah, this is a basic snippet, but I'll also give you an in-depth look at the TBT feed handler, specifically on level 2 and level 3. But this is basically, you have a pointer to data and you have the size. And this is for decoding a binary message. The decode function here is not been shown. But the basic logic is you decode and you update the book, and you call up the strategies on book update message. This is a very basic example. What happens most of the time is your strategy might be dependent on the updates on the market, or it might be dependent on its own particular loop. So, for example, if you have a strategy, if I have a strategy here, this is my strategy module, and this is my depth, and this is another thread that is basically updating the depth at any point of time. So let's call this the TBT feed handler. So what the handler can do is it can update the depth whenever an update comes, and the strategy running its loop, for example, on a rate of 100 milliseconds or 10 milliseconds, it will query this depth, and it will do its parts on sending the order forward to the OMS. The other thing is sometimes the strategies are dependent on, they actually do something whenever there's a change to the market. So here what will happen is you can basically, uh, the strategy is not going to be a separate thread that's running, but this will be something that the TBD feed handler calls upon. So what we see here, strategy on book, this on book update message. This is basically the TBD feed handler calling on the strategies method on what's supposed to be done on book update. But the segregation here is very important, because when you have an independent strategy, you have one thread here and another thread here. And if you have a common structure, then you somehow have to manage, through atomics or through uh, drop copy or swapping, that the consistency between these two components of your trading system. Uh, they do not result in a deadlock or something like that, where the strategy does not get an updated feed. And the strategy would also have, it can have two objectives. For example, sometimes the strategy would require that it does not need the exact latest depth. For example, if the TBD feed handler is currently updating this, the strategy is fine with receiving the last snapshot. And that is where we use structures, for example, swap structures. I'm not currently exactly aware of what these are called, but what you'll do is you'll maintain two data structures, and you'll also maintain an atomic bool that will basically tell you this is 1 and this is 0. That will basically tell you which of these is the current, which of these is being updated, which of these is the last state. So let's talk about this in depth later on. But the takeaway from this is the TBT feed handler can have a lot of different objectives based on the kind of strategy that you are deploying. But the most important part is you have to build the book as fast as possible. Yes, this is just a comparison between binary and JSON protocols. Anybody has I think most of the people would have an idea about JSON. Do you guys have any idea about binary or binary protocols? Okay, binary is just the ASCII representation of each character, and it's a very compact space. Uh, it's supposed to have very little, yeah, it's supposed to have a very little size, and the transmission speed is very high, specifically, because the data packet size is so small. JSON has a lot of curly braces. JSON also has, key value pairs. So each of your elements inside the JSON are defined by, it has to have a label to it. It cannot, JSON cannot work without a label for a data value. What we do with binary is, like for example, if there are two parties here, this is party one and this is party two. What they'll do is they'll pre-negotiate or through documentation or any sort of data that the message P1 will send to P2 will first contain, for example, let us talk about order. First, it will contain the order of, okay, let's not talk about the order first. The first thing it will contain is message type. It will contain the message type. And this will be, for example, this can have two or three different kind of values, but we know this will be four characters or 3 characters long. So we will read those characters and we'll move on to the next item. For example, we have the order ID and the order operation. But the order of the fields appearing inside our binary message are fixed, and that is what helps us to parse fastly through it, because we can, for example, if I only need the order ID and I know the first 4 characters are for the message type. The message type is something I'll always read to check the message type, that is. But when we talk about, for example, we talk about order quantity or any kind of field, that fourth, fifth, or sixth field that we're talking about, I can directly traverse my message just based on the information that, for example, if my code base or my client side code base requires only the fourth field, then I will skip all of these and I do not have to go through them. That is not something that can be done with JSON. Any questions? Okay.
Any example later on
Yeah, I do have examples.
with code? Yeah.
Yeah, but its main thing is when you're working with binary protocols, you'll get a complete documentation on how the data is actually structured in the message. But the main important point of this is JSON. You have to pass it as a single string, as a file, and then you have to, your parser or any kind of JSON parser you're using. For example, C++, I think is SIMD JSON is the fastest library. So what it does is it creates a tree sort of structure, and you can call upon the properties of the JSON file from that. But with binary protocol, you do not have to worry about parsing the entire structure. You can basically jump and hoop through, and you have complete idea of how the data is structured. JSON is very dynamic. You can have fields on top or above or below each other. So writing a parser for JSON is easier comparatively, not really easier, but it is slower, much slower. So that is why a lot of exchanges use fixed protocol or binary protocol. Now we're talking about the OMS, and this is, I think, the most important part. OMS has responsibilities pertaining to, accepting orders from the strategy, and it manages all of the internal communication. For example, the strategy sends an order, and it has to take care of if the order is actually sent, and if we have issues with the rate limit or any kind of problems. And it also has to give our strategy an updated view of the current status of the order. It also has to validate that the order that is actually being sent is in a valid format, has the correct values, and it forwards it to the gateway. It also tracks the status, exactly what's happening. And what will happen is your strategy here, uh, your strategy, you will have some kind of structure here that will store a status of the current orders, and this is your OMS, and both of those modules will be running separately. It is a this OMS will always be running in a dedicated thread because delays there. Both of these things are very important, so they'll always be, and they always have to manage different things, so they'll be always in a dedicated thread, and they'll be modifying this concurrent structure. These are the current orders, and you have status here, the status of the current order, and if it is being sent or not, if it has been rejected, and they have to basically collaborate on that. But another thing is your OMS, for example, here I'm talking, for example, your OMS might have fired an order, and it will put that here as a processing. Since it has not reached the exchange, we do not have an update. But your strategy might modify that order at that exact point where your order has not reached the exchange. It will reach the exchange. But just after that, you have also have to send a modification order. Just give me 1 minute, guys. My pen is not working anymore.
So just one question here. So in
Yeah.
this case, we wait until we receive the.
No, you don't wait until you receive the information from the exchange. You just fire that modification order, and you take care of everything else on your end after that. For example, if the order has failed, then you update it, and the modification will also fail. Some strategies do not require this functionality, but this functionality is also very important. For example, a lot of strategies, specifically market making strategies, do require you to modify orders very frequently. And you do not want to wait on the exchange for a response, before you go ahead and send your update, because that will increase your latency, exactly the amount of networking time it takes for your message to go from your end to the exchange end and back. Yeah, so the OMS responsibility is basically managing the order life cycle. The order has been placed. If it has been placed, if there's a networking issue, if there's uh, a kind of rate limiting issue, or the exchange has rejected the order based on some margin issues, all of that needs to be communicated by the OMS to our strategy. This is also a very small snippet, but we'll also look in detail about with the OMS code. This is basically the order manager, and it's a simple function. I don't think this needs very much explaining it. It's just a snippet for you to get a view of the basically the order. You generate an order ID. The order ID is managed by your system. You generate an order ID and you send the order, and you add that order to your local order book, open orders book, basically. Okay, let's talk about the RMS. And the RMS is a very heavy component, specifically I think the heaviest component in HFT systems. A lot of HFT systems don't really use RMS, but they do have minimal RMS for managing their strategies, specifically, to limit the exposure. And the responsibility of RMS is basically it's a middle layer between your strategy and your OMS. And what your or basically you can also implement after the OMS, but generally it is implemented sandwiched between your strategy and the OMS. But the responsibility of the RMS is, checking the limits that are currently being held based on your account margins and the exposure that you have, and the daily P&L limits, and if your orders exceed thresholds, specifically money thresholds. The RMS does not hold the responsibility for rate limiting. That is done by the order management system. And this is also a very simple snippet. It's basically, this is a simple conditional check. Order size is less than maximum order size, and position tracker dot check. Position tracker must, like here, it's supposed to be a class that basically checks if the current order is valid based on the position or not, based on your exposure. Okay, so this is something I would like you guys to understand this basic infrastructure. For example, we have the exchange here, and the exchange will send data to you on multicast, mostly on 10 gigabit network. And you have this market data receiver, and this is basically our TBT feed handler. Let's say that. And the TBT feed handler can interact with the strategies. For example, I told you in multiple ways. So, for example, strategy A, B, and C are strategies that are not very high frequency, that do not require an updates very frequently. So you'll have different structures for them, and you'll use a different code base or different kind of structures or communication mechanism for a strategy. For example, here we have fast strategy for this. And you'll also have to send this data for ingestion into a database or anything. So your TBD feed handler has a lot of responsibilities specifically pertaining to broadcasting the data further to multiple applications, and providing the data to your strategies dependent on how they are implemented, and also to your GUI. For example, here we have an example, and fast strategy D is something that's running on an FPGA card, so it needs a trigger price. Anytime that price is triggered, it will send an order to the exchange.
Abhinandan, I had a doubt.
Yes.
You said that we have to build an order or own order book after we receive the data from exchange. Is
Yes.
every strategy going to require a different order book?
No, no, no. It depends on how the strategy actually executes. If your strategy is something that executes on the scale of 200 microseconds, or so 200 milliseconds or microsecond is not common, or 10 milliseconds, or a single millisecond, then the latency part of updating the mod, you can communicate. You do not have to communicate immediately to the strategy. The strategy can use, for example, that thing I talked about, the swap structure. You'll just give the strategy an updated pointer, a shared pointer that you will update based on which of the two copies that you're actually updating and which is the last updated copy. So there, it is not very important. And the other thing is, for example, we have fast strategy here, right? And we have trigger price here. So fast strategy D works on updates from the market. So as soon as a market update comes, fast strategy D will run on market events, and other strategies might run in a loop or might run in a periodic fashion. So mostly there are only two ways the strategies are implemented, either in periodic fashion or in a fashion where they need to have the latest market update right now, so they can place an order based on that.
Okay.
Any other questions?
So in this diagram, you show that there's a feed to directly to the card, Like,
Yeah.
so, what would that mean for what use? Since like all the orders and the decisions are made from the fast strategy.
Yeah, so FPJ card, Alvin, is something that has, different use cases. If you have a very simple strategy, you will have, for example, if you can see from the, okay, you can see from the left here, right? This is connected directly to the multicast. What that means is
Yes, yes.
you might have a lot of strategy that are very simple to implement in FPGA. And for that, you'll directly route your order from here back to the exchange and it will never reach your CPU. But for
Yeah,
some
okay.
strategies that have a lot of computations that not need to be done in parallel, you can use the FPGA card to do those computations in parallel. That the CPU might not be equipped or like the CPU has a single clock cycle, but the FPGA card can run a lot of operations in parallel. So if you have some mathematical operation or you have to do some calculations that you can offload to the FPGA for a lot of instruments, then what you'll do is you'll get your price, you'll communicate that directly to the card, and the card can also be a PCI based device or it can be directly onboard your FPGA.
Okay. Thank you.
Okay.
The market data receiver is it on the same machine as strategist or it's a different machine?
Can you repeat that?
Market data receiver is run on the same machine as strategist or it's on different machine?
You can run it on the same machine, you can run it on different machines, but it mostly runs on the same machine because machine to machine latency like increases a lot. So if you want it to be running fast, for example, here market data receiver would be running locally for strategies that need to be fast, but it will also be broadcasting data to, for example, to the exchange or to the front end that's not running right here. So it's about prioritization when you're designing the TBT feed handler, and for example, you also have a responsibility to ingest the data into a database. You will have to defer those tasks, or you'll basically have to create a kind of priority that the strategies will receive the data first, their structures will be updated first based on shared memory or any kind of mechanism, and then you'll get to the database updates or sending the data over the network. No, basically the market data receiver is a very abstract term. Its job is to disseminate the data to the strategies, to the front end, or to the database, or any place else. But that is something that is defined based on your objectives. If you want to build a market data receiver that is not supposed to be saving to the database or sending data over the network, you can implement it directly on the or specifically on your with your strategy. For example, if your strategy is running on a single instrument or two instruments or three instruments, basically on a single stream, then you would not want to have to add the latency of creating a separate component that runs as an independent application. What you would do is you'd integrate it as a thread or basically directly into your strategy. Like I talked about earlier, right? Because the market data receiver is basically your strategy will, for example, which is market triggered, and your strategy is simple and it's a single thread. Then a market data receiver, the one that's actually building the order book, that thread will execute the code of the strategy.
So in the diagram, where does the order, the OMS
Yeah,
go right after in between the
yeah. The
strategy and the
OMS has
exchange?
not been highlighted here. The OMS will sit. Okay, okay. The OMS will sit here. The OMS and the RMS. They'll sit here.
Yeah, okay. Yeah, makes sense.
What's the difference between kill switch and risk manager system?
Can you repeat that?
So I understand this risk manager system also can
Yeah.
kill the order if it exceeds some threshold, right?
No, that's very platform independent, but the RMS's job is not to queue the order. And mostly that's not really done. You don't queue the orders when you're dealing with HFT, because what you do is you just reject the order or you'll throttle your strategy. For example, I work with market making strategy. So what they'll do is the order will be rejected. The strategy state would be updated to no open orders. For example, if the book is currently empty and the strategy has placed two orders and it's concurrently modifying them constantly, and the rate limit has been hit. So if the third order is placed, the strategy will see that it has placed a third order. It will keep on looking at that order. But after 1 or 2 cycles, if the order is rejected by the RMS or the OMS, the strategy, like it's not, yeah.
Yeah, yeah.
Yeah, my point is, like queuing is something that can be implemented. That's not very frequently done because it makes your code base very complex. It's much simpler to deal with just absence of data. For example, the strategy will see that the order it placed never showed up in the open order book. So it'll try to keep placing it. Whenever the throttle limit has been shot down, then your order will go through. It's a very abstract idea depending on your strategy. Like the OMS is also tuned to the strategies that you'll be working with, and also the RMS. The RMS and OMS are two components that when you are dealing with broker infrastructure, then they will be very agnostic and they'll be very robust with queuing orders and all of that. Mostly, I don't think they queue orders. Even Greeks, they basically reject the order. You have to place the order again. But yeah, queuing is something that can be implemented. But in mostly HFT systems, the OMS and the RMS are custom built, to serve the strategy.
Hey, one quick question.
Yes.
Will you be talking more about how to transfer the order book updates from the market data receiver to the strategies, like using lock-free queues or
Yeah,
like you
yeah.
mentioned,
Like
some kind of swap?
this is a very comprehensive program, around 30 to 32 lectures. So we'll also go into detail on how that is actually implemented and what are the like I'll also show you some code bases today that will help you understand the flow of how I implemented some things like for example sending these updates to the strategy and the kind of structures that are defined to do that. Uh, yeah, I'll also go into detail into that.
Yeah,
I'll show
because
you
that
the
has
code.
been the tricky part, right?
Yeah,
Because multiple threads accessing a shared state. So,
yeah, there are myriad of ways you can do that. You can use a lock-free queue for that, just sending the updates, sending the complete market depth over. And I'll also like tell you about the solutions I use.
okay,
Yeah, but
thank you.
we'll go in depth about all of that on how the OMS is basically run and how the TBT feed handler does stuff. Yeah, so let's talk about the order book data structure. Well, the objectives or requirements for our order book data structures, we need to have fast insertions and removals, and our order book needs to be sorted by price levels. For example, if my client or my strategy is calling market depth and it's inputting a token, and after that it's calling a function on that. For example, get price level 0, get price level 1. All of those have to be very fast. We can also have access by order ID, and access by order ID, I mean when our strategy requires information about specific orders. It's a very general thing. We can use the best thing we can use an unordered map and vectors. But there are also many different implementations. You can also use linked list implementations, and you can use array-based implementations. Vector is basically an array, but like the problem here is unordered map and vectors are both dynamic data structures or data containers. Dynamic in the sense they're stored in the heap memory, and the size of those are determined at runtime. So those are particularly slower. The better answer would be, I think the better thing would be like using unordered map is fine, but for vector we can use fixed size arrays. Stud array. Stud array is basically an array, but like if any of you guys have used C style arrays, uh, basically the size pointer decays as soon as you pass the reference, and that is something that's available with std array.
Can you repeat that, Abhinandan? Like STD array?
Yeah, we'll talk about this a lot more in detail. But the point I'm trying to make is we'll talk about dynamic heap memory and stack memory. But basically, stack memory is, for example, if I declare in my code I have an array, I use this vector and I create a vector of integers, and I do not give it a size. My program can keep on adding to this vector without worrying that it will reach its maximum size, right?
Yeah.
Yeah, so that comes at a cost that the size of this is not determinable during compilation time. So the compiler does not know the size this vector will be, and so it has to use the runtime memory or heap memory. Heap memory is basically a large store of memory that can also grow in size. Stack memory is what the compiler optimizes a specific area of memory. For example, if I would have used an std array in 10, then the compiler, while compiling my application, knows that uh, what I'll need is an array of size 10. So
Yeah.
it can put it into the stack, and it does not have to dynamically regrow. So that is where the benefits of fixed size data structures come from.
Okay. Okay. Got it.
Okay, so this is also a very basic code snippet, update, and these are very simple functions. Messages insert, cancel, modify for a specific market depth. Then you call those functions. This is also valid for orders. This is more valid, I think, for orders. Because for order updates, like we talked about NSE updates at the TBT co-location or level 3 data, you'll get that this message or this order ID has to be removed, or it has to be inserted, or it has to be modified. Yeah, so here is just a basic summarization of the roles of the feed handler, OMS, RMS, and the gateway. Gateway is basically the interface, but I think this is plenty clear, so let's move ahead. Okay, so let's talk about messaging protocols. Messaging protocols, like I talked about, fixed protocol or binary protocol, they have a lot of impact on the amount of time you need to parse the message and the amount of time the packet or the size of your message is affected. So the time it takes for a message to reach back and forth from the exchange. So it facilitates communication between trading systems and exchanges, and it defines all of the formats for your order, uh, for sending the order and for receiving order updates, any kind of trade confirmations, and your market data feed. Okay, so here we're looking at a fixed protocol structure. And your fixed protocol structure is also defined in, uh, it is a predefined format. If you ever work with fix, you will see an XML file that defines the protocol, and you can directly import that and use applications, for example, quick fix or fix8 to directly pass this structure. Not very important to understand exactly how this is defined, because this is very much dependent on the kind of exchange you're working on. But it also contains key value pairs, and it ends with the checksum. What the checksum does is, for example, if there's a bit flip between one of your packets and one of the values gets modified, the last value here, for example, 10 equals to 157, that is something you'll take the entire message and you'll calculate the checksum. And if it is the same, then it's a valid message. If it is not, then you'll ask the exchange for a snapshot. A snapshot again, for example, you must have lost some kind of semblance. So the further updates you cannot process because you have a missing update that was corrupted. Yeah, binary protocol is similar to fixed protocol, but it works on, as I told you, and ASCII characters. It's compact and its size is very fixed. Mostly it is very much fixed. That the exchange will send you a message type, and as soon as you receive, as soon as you read the first 4 bytes or the first 8 bytes of your message, you know that the rest of the message is going to be either 16 bits long or 28 bits. And it is the main protocol used in any scene has that. So it is very much optimized for low latency and high throughput. Yeah, so this is an example of a binary message. For example, the first 4 characters here define the type of order they'll be. I'll also show you, like, just give me 1 minute. I'll show you some NSE documentation, the NSE NNF documentation.
And oh, join already.
Okay, so this is NSE documentation for the TBT feed handler. Yeah, like as you can see here, we have real-time data, market feed level 1, level 2, and level 3. But the important part is they've defined the data types. For example, if it's a character, it'd be a size of 1, short will be size of 2, long will be size 4. And here we have the data structure details. So as you can see, they are defined by basically size of the character, and you can hop from item to item. For example, if you only need for example, here we have info data, and if you only need the expiry date, you know how many characters you have to jump with your messages that are pertaining to data. So you can directly get the expiry date or the strike price. So it's a format that has been defined preemptively. So it is much easier for you to, traverse that. Much easier to traverse the message compared to JSON. Also, this is a very basic code snippet of, how do you avoid passing a fixed message. And you'll also, you'll have a map of integers, basically the fields that are present. You'll create a string stream, and then you'll constantly read into that and add it to the fields map. And this is just this is a very basic code snippet. But let's get to the actual code. Okay, so if you can see here on the left, uh, I'll look at the code for the web socket. And here you can see there are four classes, right? There's a definitions, there's a market data client, there's a trading client, and there's this WebSocket connection single file. So the WebSocket connection single file here, uh, yeah. The task of this file is just maintaining that connection and send messages as fast as possible. For and also logging. You can hear in the send message. Are you guys aware of async IO in C++?
Yes, I am aware.
Okay, so in C++, async is done differently than languages like JavaScript and Python. Okay, I see some messages in chat. Yeah. So what C++ basically does is you create a dedicated thread uh, that is supposed to manage our async operations. Here I've used boost.beast and just give me, just these are the public functions, right? So what the send message function here is doing, and it is scheduling a task inside my event loop. So, basically, if my connection or WebSocket is lost or it's not connected, it will throw a runtime error. But if it's connected, I have this connection info and a pointer to a write queue. And this write queue is basically a atomic queue. This send message function, this WebSocket connection class has been built so that multiple strategies can directly access this and send messages to it. So what will happen is this write queue and this current function, uh, this needs to be thread safe. So write queue is basically a atomic queue. And if my write queue size, I am place the message into the write queue, and if I see that the write queue size is equal to 1, I'll perform a write operation. But it can also happen your event loop is already processing that message. So like I'll go to the bottom here where the private function is defined. Yeah, here is a do write function, we will call it, right? So what it checks is first checks if the queue is empty. Like since this function can be scheduled by a lot of different threads, that can basically call this function, call the send message function, and do write can be triggered multiple times. Oh. Yeah, so it first checks if the queue is empty, and if the connection is broken, then if the connection has been closed. Okay, yeah. So if the connection has been closed, then it returns, and it uses a shared pointer to manage the life cycle. For example, here we're not using any kind of dynamic memory allocation or, for example, allocating new memory for the message. What we're doing is we're just using a single structure. For example, the message has been defined in the stack, and we're taking that message from the queue and we are making a shared pointer here. Shared pointers live as long as there's an instance of the shared pointer that's still pertaining. So when this function completes, if I've not used a shared pointer, then the next part here, for example, here I'm using bind executor. Bind executor is basically like we can just think it of scheduling. Boost ASIO is the async IO library, the standard library for C++. But what this is doing here is I'm giving it this, like forget this connection strand part. Need to use a pen, I think. Okay. Very bad with touch screens. Like let's forget about this connection info.send strand part, but this is basically scheduling a task where for in the bracket where you're giving capture variables. So it will have access to this specific class instance or this object. And we're sending in a function, basically a callback function that will be triggered when the async write to this buffer has been completed. And when that happens, for example, if my message has been sent, here I'm calling async write. Async write is basically it will send the message to the exchange. After the exchange, after the message has been sent over, this next callback function will be triggered. And if you can see here, if I have an error, I call a different function here, handle reconnection. And if the write queue is not empty, like if you can see this uh, bottom line here, if not connection info to write queue dot empty. So if my write queue is not empty and if I have further messages to process, I'll call do write again. Instead of going through this entire cycle of callbacks and all of those, I'll just what I'm trying to do here is whenever there are multiple messages or messages queued, this function will specifically not be interrupted. And I do not have to schedule another async task to process those messages. This will again trigger do write, and do write will again check the queue, and it will send the message again. So this complete file here, this manages that connection, closing connection, and there are a lot of functions that you have to write when you're working with production level code. You have to work with pinging and all of those, and you have to synchronize all those into a single thread. And you have to keep all of this behavior isolated in a single class, specifically for the fact so that you can have some semblance of idea where the errors are coming from. For example, you can see here in all of my logging, I've placed here WebSocket connection exception and read handler. So I know that where the exception has been thrown from. And I'll also go into a bit more detail about the connection part, the do connect function. So this is the function that is first triggered from this public function. I'll just give it connect. Well, what connect does is it posts a task to my async IO loop that run this function do connect. What the function do connect does actually, it checks if the current connection info.ws object is active or it has a connection. And if it does, it tries to close that connection. If the connection is not able to close, it calls a reset function. It basically, empties that WS or WS variable. Then it create. Yeah, then it creates another object that it basically a WebSocket object, which is basically a shared pointer. And we have this WebSocket stream, beast, SSL stream. This is not very important. You'll use these classes or something with another library. But what it does is it first calls the resolver, which basically takes my URL and give DNS servers you must have heard of. So it basically gives me the exact address of where I want to send that. But the resolver part is also a networking part, right? Like I do not want my loop to just stay put and not do anything else while my resolver is working or while I'm getting some response. So what I'll do is I'll use this function async resolve, and what this basically does is when we have a response from the resolver, then trigger the following function that we've defined here. And that is we capture these two variables, we capture this and the WebSocket that will be used inside our function. The TCP endpoint, and these are defined like this arguments, beast error code and TCP endpoint, those are defined by this function. Get lowest here. No, I think I'm down. Yeah, async resolve. Here we get the error code, we get the result type, and we also set a timeout on the operation. And you can see here the comment make the connection on the IP address we get from the lookup. So the IP address that we get from the lookup, we try to connect with that. Here you can see if error code, then handle reconnection is also another function that gets triggered. All of this is mostly network heavy code, but the important part I'd like to highlight is, give me 1 minute. Yeah, so since we have this single thread here and it's running a loop and we have to do all these operations. So this loop can never be interrupted. So the flow of our application is mostly whenever we have a task that needs to make any kind of connection, for example, resolving or making a connection, making TCP connection, and then upgrading that connection to WebSocket. All of those tasks are rescheduled on this particular event loop instead of handling them sequentially. So these are basically chained together, where for example, when we're resolving, we basically tell what to do after we have resolved. And this function where we're connecting, we tell them what to do after the connection, after we get a response from the connection part. Any questions there? No questions? Okay, so this complete file, yeah. Okay, I think somebody was asking something. But this complete file here is specifically to encapsulate all of the networking components. So the rest of the components do not have to deal with those. Now let us talk about the market data client. Yeah, so the market data client here is basically what our end strategy would mostly use to give me 1 minute. For some reason, collapsing function is not working. Yeah, so as you can see here, I have this template right here. It's a templated class. So the reason for the templating is, the compiler knows that my structures here, where our strategy is actually using this to compile the application. The strategy when creating this market data client would have to give integer value for the market data depth and a Boolean value if you want to be logging or not. So at runtime, these variables would not be defined. They will be basically coded into the assembly. And here I have the constructor, the connection basically connecting to the Kraken API. And we have to maintain two connections, one for the unauthenticated channel, for the level 2 market data that anybody can access. And we have this other URL specifically for level 3 market data. I'll just go to the button, tell you, show you the data structures that have been used here. This code can be more optimized, but specifically for this use case, it was not necessary. So what I've used here is, you can see, I'm maintaining here a concurrent unordered map. TBB is a library threading building blocks by Intel. TBB, if you use TBB concurrent unordered map, you do not have to worry about multiple threads modifying or changing a single value or adding to the map or deleting values. So here I've defined a data structure. One of the first part is a string, which defines the instrument. And then I have this unique pointer to a thread safe container. This is a structure that I've defined. And what this structure basically contains is the order book level 2, uh, basically the market depth, level 2 market depth for any specific instrument. And the same goes here for level 3. And as you can see, this is a unique pointer. And the reason for that and this thread safe container is whenever my strategy is looking for my market depth, I do not want it to go through this unordered map. What I would do here is I've defined a function here that here you can see here. So get pointer to level 2 book container. So once my strategy's thread has an access to the pointer, it can skip all of this going through the map and going to that data because it is a persistent data structure. What I'll do is I'll never modify the map because that is very expensive and costly. It will cost me latency. What I'll do here is my strategy has also like my market depth updating part that also has a pointer to the level book container. And this also like my strategy will have a direct pointer to the thread safe container for level 2 book and level 3 book. And what this basically does is if the order book it's empty, it does not already have that element for that simple, it will create a container for it. Now let us get to the market data part. All of these are functions for sending messages to the exchange, sub trades and subscribe to HLC. Now this is a very important function. Any message I receive from my WebSocket connection client that I'm using to basically connect with the exchange that is specifically for market data, I will receive these messages here, and you can see I have a switch case here to trigger the function that I want to call. So here I have if I get a heartbeat or status, I do not do anything. But if I get a ticker, I call my function pass ticker. If I get a book order, I use the level 2 pass order book level 2 function. If I have an orders and a level 3 order, I use the pass order book level 3. I call this function. And if it's an OHLC, I call OHLC, and similarly for all of those. And here is the function that basically parses the JSON file. Passes a JSON message update order book level 2. Level 2 is basically what I talked about, where we do not have individual orders, but we have a price and the quantity at that price. So what this does is I'll show you just the structure that I've used for. So this is the structure that I've defined for order book level 2. As you can see, all of these are compiler directives for align 64, so that none of these arrays, and I have not defined a fixed size here because I'm taking the size from this templated variable, and this size is defined as you can see in my market data client. I'll use this. Yeah, see here I'm using market data depth, right? So this goes all the way back to our initial initial argument that has been taken from our strategy code. So all of this is done at compile time. So this does not slow your program down. But this is a dynamic way of basically propagating the size or anything else you want. Book entry. This is the book entry class. It's basically the price and quantity, and I've just modified some operators. Key. For example, if I'm using the equal to operator, comparison operator. So I'll just compare the price. If I'm using the lower than or bigger than
Abhinandan,
comparator, I'll use the price.
I had one doubt.
Yeah.
The Kraken API that you told us about, that it is
Yeah.
going to, we can use a free tick to take data,
Yeah, you can
but we
you can
won't
use
be
level 2 data.
but we won't be able to use, like we won't be able to simulate like the latency that we need for HFT, right? Because we are getting
See,
the
Nikhil,
data. online?
The important part for us to learn here is like measuring the latency it takes when the update comes to us. And after that, how long does our code take to build the order book? That is the latency that is relevant to us specifically right now, because we're not trying to run a strategy. We're just trying to be better coders who
Okay, the
can,
time that we receive the price
yeah.
and to the
For
time we
example,
take to build our order book,
yeah, for example, here you can
right?
see
Okay.
this. I'll just show you. What I'll do is I'll create a timestamp somewhere around here where the message was received by my application. Or, even in this parse order book here, I just, also you can see this auto now, right? This is specifically for logging to see how long this particular code here where I'm updating the order book, it takes place. So, if my logging is enabled, then I'll also print the time it took me to process the order book message. So the important part in latency here is it's not important for us to simulate how far we are from the exchange. It's important for us to know how fast we are doing our responsibility. It's either be it making the order book or sending a message, sending an order message.
So, what should be our target like in terms of time?
See, it is very much dependent on the kind of data you're working with. So you'll not you cannot just target 1.5 microsecond latency of order book based on some exchanges will give you data in format where it is possible, and some exchanges will give you, for example, they'll send you unsorted data. They will not guarantee that if they have sent 4 updates, then they will be sorted, and you have to take care of that in your code. But if they tell you that their messages will be sorted, then you do not have to take care of that. And in that case, your latency would be higher. Sorry, your code would be faster, where the exchange is helping you out on something. So sometimes the exchange will not help you out. The exchange will just throw data at you, and where your application has to do more processing, you cannot set some kind of target latency. It's more about looking at your code base and constantly optimizing it. For example, here what I've done is if I show you the my function specifically for market data, these definitions, right? Yeah. So the function for the level to book, I've not used a linked list or anything. All I've used are standard arrays, and with this book entry structure, it only has 2 doubles, price and quantity. So a very compact structure, and I've created 4 arrays. I've created bid array, ask array, updates array, and this merged array. And what I'll do here is this is basically I have this function batch update side, and what this does is most of the time it is a very normal thing to assume that 90% of my updates will be happening at the top of the book. So given this information that I know that most of the updates will be at the top of the book and most of my latency will come from updating those values. If I use an array and I access the first and the second element, and basically if I have to modify an array or, like you can see here, the merging process. No, as long as what I'm doing here is what my function in this class, what it's doing here is it's querying the order book container, the thread safe container. And in that container, okay, it's update, right? Yeah. In that container, it basically uh, it basically placing the updates inside that updates array. And what it's doing is also updating the size. Basically, if I have 2 updates and I have this fixed size array of 10 size, like for example, here I've defined here with a fixed size and I have defined with a size of 2. These are maximum sizes, but I also need to know the number of updates I have. So here I'll also store the size, and I'll call this function book.updateBits.size. So update bits does not need to have the updates. The updates have already been stored in its structure in this updates array. And I'll use this merged array to the merge process here. As you can see, if the price is equal to the update, keep the updated entry. And what it does basically compares both the arrays. I update side size and update size, right? So it basically it goes through both of those things. Forgive me, this is a very this is something I worked on a long time ago. Yeah, but this is the side size, the side we're updating, either bid or ask, and this is the size of the updates. So which of whenever our index goes above those, any of those, then we're supposed to stop, right? For example, if our update size is just 2, what we'll do is we'll compare this uh, the price of our current the first element with the size of the if the price is the same, then we'll keep the updated entry, and in this merged array that's empty, we have this variable k that I think it begins with 0. So merged keeps us the updates that are supposed to happen, and we'll push the value of our update when if it is equal in price, then we know that something must have been updated, either volume, and we keep the updated entry. And we go I plus plus because skipping we're moving on to the next element of our bid or ask array. So here you can see side size. It always compares the size of the side. And if our updates and side, if it is higher or lower, then we either keep the value of the update or keep the value of the side. So, we for example, I'll just use my pen here. Yeah. So we have these three arrays. These are updates, and this is our array, which is basically bid or ask, and we have this merged array. So what I'll do is I'll go through these one by one. I'll compare both of these elements. If I see my price has been matched, the updates, I know that since this is level 2 data, any price that is inside the updates is going to be inside this my final array, right? But some entries from here might not have to be taken into account into this merged array. So what I'll do is I'll traverse through these one by one. For example, you can see here while I is less than side size, side size is this basically size of 10, but it can sometimes be lower. If you don't have enough orders and you're looking for a depth of 10, it can be lower. So you have to handle that edge case. But in this case, if our side size is almost always fixed, we do not need this. But this is something we need to handle it in the cases where our market depth might be lower. And we're comparing as long as both of these arrays have not been traversed, we will compare them. And we'll compare the price of the first element of our site with the update of the with the first element of the update. If the price is equal to it, we'll keep the we'll keep the elements from the update, and we'll use this I plus plus to just skip this element and move on to the next one. And if we compare these two values, and like depending on if the update is higher or lower, we'll either keep the value from the update and move on to the next update, but not move this pointer that we're traversing in the our bid ask depth. And if our side is on the lower price or higher price, this basically dependent on if we're looking at bid or ask array. For example, in a bid array, the price keeps on decreasing as we go down. In the ask array, the price keeps on increasing. But let's just assume about the ask. Let us take this as ask. So in ask, this is the lowest price. And if our update this has been placed, we'll move on to the next update. We'll compare it to this value. And here you can see the comparison. We keep one of those values, but we do not skip that value. We only skip that value when our value, for example, this value is equal to this current update value. So when those are equal, we know that this is the only important part and we can skip this. And after we have, merged the array, we just copy this into our For example, any remaining updates are left and the market depth has been finished. This is basically more or less handling the edge cases. And I'll use a stood copy. Stood copy is a fast way to fast way to copy values, especially from array to array. And like we talked in the last lecture, I think, yeah, in the last lecture we talked about prefetcher and all of those. This is where the prefetcher part comes very handy. Because we're working with arrays, but we're traversing them in a linear fashion. So whenever I'm calling when I'm accessing the first element, and since my first element is basically like I showed you a single two double values, then I know that instantly the rest of the elements have already been loaded in the cache. And same goes for the bid or ask side array. Any array that I call, the elements have already been loaded. So it's faster, relatively faster. And I know that my updates are mostly going to be at the front side, since those are where the most modifications happen. So that will give me an average latency of very little. Most of the updates always happen at the top of the book. So I'm the part that I actually need to worry about reducing latency is at the top of the book. I can take the penalty that if I have to update this last only if my updates contain an update to the last value of the book and I have to traverse the entire book. But I know that is something that's a rare case. That's not going to happen. Yeah, so mostly you can see here market data client handles all of this. It also you can see here it triggers this function on level 2 response. And this function is defined here. This is something that I receive from the client application. See, I've defined all of those as null pointers, and these functions will be assigned by my strategy. So when I was talking about when a strategy has to be triggered on a market update, the strategy would just fill these values on subscription response or on ticker response, and it can fill any kind of code into these functions based on its own file. But they will be triggered by this market data client. But if my strategy needs an updated view of the book, it can have this pointer here, like here, this get pointer to level 2 or get pointer to level 3 book container. And it can directly access the book anytime. We'll also move into a lot of different structures later on. I have this I'll just show you. This is an object pool. It has a maximum capacity. But this is specifically where, for example, in your code, when you have to parse something and you have to create new instances every time, what this object pool will do, it will basically have a pool of those objects already ready. So the time wasted in creating an actual object, for example, a parser or, for example, a string stream or anything like that, this is a templated class. So it has a maximum capacity, but it will keep on adding to this. And once you've used that specific object, you'll release it, and it can be just picked up by another thread or basically any other thread. And instead of declaring a new object in that thread, I can directly pull from this pool. Any questions, guys?
I saw the TBB queue there in the code somewhere. Are you using the
Yeah, threading
yeah?
building blocks by Intel.
Oh boy.
That's not a very if you are very latency critical, you will not be using TBB. You'll be using your own implementation. You'll basically be
Yeah.
using unordered map with pointers. But in this case, the distance from the exchange was not as important for the client.
Okay.
So I've used TBBQ. They had latency constraints. So for me as a developer, I would not go about optimizing for something that the client does not care about.
Right. Makes sense. Yeah.
Yeah.
So just to clarify,
Yeah.
the order book levels that you created were more to have like detail levels of the orders. Is that it?
No, the code I demonstrated to you was for just give me 1 second.
Yeah, but you had like order book level 1, 2, and 3, and then like
Yeah, those are
they
defined based on the exchange. So basically, I do not have level one. Level one is basically trades. Okay, sorry, my pen is white. Level one is trades. Level two is this book I talked about where we have price and quantity. And level three is we have here price and orders. So what will happen is here we have price of 100 and we have a quantity of 10. Here we'll have a price of 100 and we'll order ID 1 with a quantity of 4, order ID 2 with a quantity of like 4, and with 3 with a quantity of 2. So you have this granularity of information when we're working with level 3 data.
yeah, okay. Wait, so why do you need this level of granularity?
Specifically, like you can use snooping to check iceberg orders. Like it's very much dependent on the strategy. Some strategies might be working on snooping data or basically looking at the size of the orders at a specific price. Uh, but like yeah, it depends on the strategy. Mostly depends on the strategy for to have this kind of data. This does have some information, uh, like some extra information about the individual orders that are present and the bifurcation. Whether or not that information is useful depends on your strategy.
But since like both ways are in the same price, if there's like the opposite side to fill, I don't know, 5 quantities,
Yeah.
wouldn't it be like the same result that in the end, like both ways?
No, it'll be the same result in the end, but you're not really trying to fill orders most of the time. What you're trying to do is gauge where the market is, and you're trying to place limit orders based on that. For example, here's the 100 price, and this is, for example, this is the ask book, and 100 is the best price. So what I'll do is I might look at this and I'll place an order for a single lot here at 99.9. Like this is just arbitrary stuff. So it depends on the a lot on the strategy. And like forgive me,
Oh,
but the strategy parts are not really my forte exactly. The quant strategy and the kind of data they use.
it's more that if you have more granularity, you
Yeah,
can
it's
move
just
around more like each one of the orders. Is that it?
yeah. See, Mathus, both of us can speculate on these things. For example, what can be done with this information, but I don't have the credentials to talk about how useful this information is or how exactly this will come into hand when you have a quant trader who's working in working on HFT strategies. So
Yeah,
that's my
okay.
point. Like this is information that is provided by the exchange if you want that level of granularity.
Mm-hmm.
Whether it's useful, whether you need it or not, that is like I don't know about that very much and
Yeah,
how it
okay.
would be useful. But I think some strategies do use it. Market making, I've mostly seen. I've like sometimes people use these things. I work with people who can look at the order book and see these orders are, for example, a person I knew. He worked in a company in a firm, this quant firm, and after that he went to a different firm that I was working with, and he could see the order book and he could tell that these orders were being made by that specific party. So,
Yeah, okay.
like, take that information as you will.
Mm-hmm. Each one does what they want with the information, right?
Yeah,
Um,
our
mhm.
job as developers is to, disseminate this information as fast as possible, and like provide this information for the end client.
Yep. And also, are you gonna like make it available, the code available in the drive, or like at least like a snippet or something like that?
Can you repeat that, Mathis?
Are you gonna make the code available in the drive?
This code I'm not going to be able to make available in the drive. This is proprietary.
Uh-huh. But
Yeah,
I
but
mean
I can
something
give you
similar
snippets.
or yeah, something
Yeah,
similar or
I'll
something
just
like
look
that.
for some examples. Like it's very easy. You can find a lot of examples on how to build the order book. It's dependent on the exchange that you're working with. And Alex here, it says it's not about nanoseconds. It does run in microseconds, but that was not the requirement of the client. So that is why uh, I I I did not do extra work to optimize specifically for that. Can you please run the code explore? Like it's difficult to understand. Yeah, we have Souvik, sorry. We have a lot more classes that we have to do. So in those classes, I'll also explain the code in much more detail. Maybe not specifically this code, but I'm also looking at some kind of exchange simulator that we can use to build for example, our OMS and TBT feed handlers.
How many order books are you maintaining currently? Like how many symbols at one point?
You can maintain like as many symbols as you want.
Right. No, I mean in the code that you were displaying,
Yeah,
is there?
you can maintain as many symbols as you want. TBB concurrent unordered map. It does not necessarily require a fixed size. So,
Mhm.
for example, if my strategy is subscribing to a new instrument, then the strategy is starting. So at that point, allocating new memory is not much of a problem as long as when I've allocated that memory, I get a pointer to it. My strategy is actually running, it has a pointer to that. Then I can keep on allocating memory. So I can use this unordered map to increase the memory or basically TBB unordered map to basically keep on adding symbols as many as I want. This is not
Yeah, because
exactly a very like nanosecond level of code. This is much more on the few microseconds level.
yeah.
Yeah,
No, the more symbols you have, right, in the order book,
yeah,
and sometimes let's say you miss a packet, it's a
yeah,
big problem because then you have to go into the recovery mode, get the snapshot, and start
yeah,
building your order in, right? Something like that. I don't know. I'm not exactly sure,
yeah, yeah. No,
but
you're pretty accurate. Like this is what you have to do with NSC. But like for example, here what I've done is I'll show you. My screen is this screen is being shared, right? You guys can see the code.
Still, we can see
I
the people.
No.
Okay, okay.
so you basically have two feeds coming in at all times. One is the updates, the other is the snapshot, right?
No, no, no,
Just in,
no, 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 not two feeds. Anytime,
no.
yeah, just give me 1 second. Must be a function. Yeah, checksum. Yeah, basically what will happen is my checksum fails. Then I'll not release. This release buffer is basically a lock as long as my function is updating the order book. But what I'll do is my checksum verification fails. Then basically I'll keep this buffer on and I'll call for a snapshot. I think function there. Okay, this might not be the updated code base. But what you'll basically do is you'll resubscribe to the instrument. You'll unsubscribe and you resubscribe. That is the solution that like that is specific like as I talked about, is very specific to the exchange that you're working with. With
Mhm.
NSE, it's a different thing. You have to get the snapshot and you have to for example, you have to record the last sequence number that is in the snapshot, and then you have to apply the all of the updates that have been fired at you after that.
Right, right. Something similar with MDP3. It's just that they have a continuous snapshot stream also, right? Instead of updates, you have so you subscribe to both at the same time.
So you're talking about MTBT.
MDP3, CME.
Okay, okay, okay. Okay, so they have a
So
snapshot stream.
they have a snapshot stream on a different port and a update stream on one port. So you subscribe to both. And that snapshot stream is basically a backup plan, right? In case you miss a packet.
Yeah, yeah, the snapshot stream in this case would be a it's a much better solution than making a TCP request like we have to do
Yeah.
with NSE or
Right.
like here also. Also, there's a Kraken exchange. This does not use this uses WebSockets. So when you're using WebSockets and you're using JSON files, your latency is already down the drain.
Yes, yes.
Yeah.
Yep. You should avoid parsing JSON at all times. That's just not
Yes,
going to.
yes. Yeah, it also Kraken exchange also offers fixed protocol. But still, that is also traded through WebSocket. Your market data, incoming market data is through WebSocket, and WebSocket uses TCP IPs. So you have to go through all of those. You have to, for every message, you have to send and receive the acknowledgements, and that's already slow. Even if you're
Yeah,
using binary or fixed messages, you'll still get a lot more latency than UDP. UDP is basically
right,
firing packets at your machine.
right. Yep.
So, Abhinandan, I
Yes,
was
yes.
trying to test a little bit and like explore a little bit of data to just to see and check some things. So, uh, I extracted the like in a span of 2 days, the historic bid and ask books of one specific instrument, and I was checking that there are some ticks and some data points that the timestamp are exactly the same, even in the nanoseconds, and but like the books are a little bit different. Would you happen to know if there's anything that could cause that, or I don't know, it's just like
Well,
data.
did you store this feed yourself, or are you working with some data vendor that's provided you
Yeah,
the data?
it's from a vendor.
Okay, and like you're working with crypto data or anything like that?
Oh, it's stock, regular stock listed.
Okay. I'm not aware of that. That can happen, but
Mm-hmm.
like mostly uh, when you're dealing with, for example, when you're dealing with NSE, you have a sequence number. So you know that same sequence number can never appear twice. So even if you have a nanosecond timestamp that's the same, you apply them in order of the sequencing number.
Mm-hmm.
In your case, I think you'll have to like apply the updates that have come after that, even though the nanosecond timestamp is the same.
Yeah. Well, it's just that I don't know, like from
Like for example, if you need
timestamp
to
to
check,
timestamp.
Mathis, if you need to check if there is some discrepancy in the data, then you can see that, for example, if you have two depth snapshots with the same nanosecond, then you can check, for example, if something might have changed in the market, for example, and the price has been modified and the order has been missing and the depth has been shifted up, then you can kind of gauge at the fact that, yeah, this is fine data. Like it's a very big problem getting very accurate and reliable data, also here in
Mm-hmm.
India.
Mm-hmm.
But like same nanosecond timestamp, I haven't really worked with all of that. Like I've worked with sequence numbers and here
Yeah.
in this Kraken exchange, I might have received updates, but since I'm working with a live feed, so I apply the updates sequentially. So,
Mm-hmm.
your question might be about the quality of your data. I cannot assert into that.
Yeah. Oh, okay. Thank you. Bye.
Okay, guys, any other questions?
Hello,
Yes, Yashpal.
so my question is that would there be some more session on C++ core topics like memory management
Yeah,
and
there'll be a lot of
other?
lectures about C++. Pranay must have shared the syllabus with you guys. So the next lecture will be learning about the Linux infrastructure and how Linux manages its network stack and how we can optimize the Linux network stack. And after that, just let me open the syllabus. Then we'll move on to module 2, which is more about operating systems. Yeah, but just to answer your question, Yashpal, yes, we'll be working with the like all of the optimization that we can make in C++ and how stack memory and heap memory works and how we can optimize our code for all of that.
Yeah, thank you.
Any kind of things
And
we can do for compiler optimization to system optimization.
yeah,
But we'll have to go about it step by step.
yeah, and this session I find it more difficult to consume. So would be there some more implementation uh,
See, I
around
completely
that
understand.
or
The point of this lecture was not to more or less showcase the exact implementation of the TBT feed handler. We have that for a separate lecture. The objective of the lecture was mostly to gauge at the responsibilities that the OMS and the TBT feed handler and our RMS have in our system. So what they have to do and the different ways we can go about taking care of those responsibilities in our code. For example, the TBT feed handler, its objective is to disseminate the data, but its objective is also to give our strategies a very concrete view of what's happening in the market. And the same goes for our OMS. OMS has a lot more responsibilities than the TBT feed handler. The OMS has to manage the orders, and the OMS maybe it's supposed to have facilities like throwing multiple modifications at the same time, and throttling those based on the rate limits. But more or less, the point of today's lecture was to understand the responsibilities that the client-side components, the OMS, RMS, and the TBT feed handler have, so we can reason about how we can design our systems to better suit those responsibilities and design it in a faster. So we'll go much more in detail about how to build the market depth and how to build the OMS. Yeah, so today's lecture's objective and what I talked about is clear, right?
yeah, thank you.
Okay, guys, since nobody else has any other questions, I think we can end the lecture.
Yeah.
Okay, thank you, guys.
Thank you.
Thank you.
Thank you.